Assalamu alaikum everyone. In this video I would like to share a way to describe a finite state machine using Verilog. So in this example I pick the 101 sequence detector. So first I will show you how to construct the Verilog module for this 101 sequence detector, and next I'll show you how do we compose the test fixture so that we can get the simulation results of our 101 sequence detector. So as we know, to realize a finite state machines, there are two methods, in which the first is by using Moore machine and secondly by using the milli machines. So I will show you both approach in getting the Verilog module of our sequence detector. So the key to get the correct module for sequence detector using Verilog is by getting the correct state diagram. As long as your state diagrams is correct, so basically there will be no problem with your Verilog module. So here I already have my state diagram for 101 sequence detector. Alright, so on my left is the state diagram for Moore machines, and this one is the state diagram for the milli machines. So as you can see here, when the system get the sequence 101 throughout this flow, so in state 3 the output is high. So similarly in milli machines, so basically we can say that S2 and S3 in Moore machines are combined. So in milli machines we always have one less state for sequence detector in particular. So when we get the 101 sequence, the system gives output high. Okay, so now we are ready to construct our Verilog module based on this state diagram. So we will begin with the Moore machines. So let's create a new project. So let's name our folder as the sequence SEQ sequence, perhaps DET detector 101. So choose the top level source type as HDL, which is either Verilog or VHDL. So proceed, and we can just proceed with this step and finish. So now we have the folder which is known as SEQ DET sequence detector 101. So right click on here, choose the new source and pick the Verilog module. Now we want to begin with the Moore machines for 101 sequence detector. So let's name our file as Moore 101. So proceed. So in here we can utilize this wizard to specify our input and output. So we have basically a single input and single output, but beside the output we also require the clock signal and the reset signal. So let's name our input as X, and then we require the clock and we require the reset as well, and our output is, let's say, Y. So we specify y as the output. So we proceed with the next step and click finish. So we get the skeleton of our code. So as you know, we can always combine if we have the input or output with similar number of bits, so we can combine them in a single line. So clock and reset, it's supposed to be reset, so we can remove these two lines. Alright, now we already have the input and output declaration, so we can proceed with the body of our module. So first and foremost, we need to understand that when we deal with a finite state machine, we need to consider the state, or the present state and the next state in particular. So instead of declaring the input and output, we also require to declare the states. So before that, since y will be utilized as the data storage elements, we have, instead of declaring y as output, we also need to declare y as register. So in this line we declare y as output and also register at the same time. So back to the states. So we have to declare our present state and our next state as register as well, because the state is basically the data storage elements in which it retains its value until the next value is assigned to it. So register, so let's name our present state as CST, current states, and our next state as NST. So CST is current state or present state, you can call it present state, and then NST is our next state. But we have to be careful here, because our states, we have 4 states in more system and 3 states in MIDI system. So in order to encode these states, we require a 2-bit parameter or 2-bit number. So if we call S0 as 00, S1 as 01, S2 as 10, and S3 as 11, that means we require 2-bit parameter. So we have to declare the register 2-bit for our current state and our next state. Okay, next is declaring the state S0 up to S3. So we can use the parameter type. So we have S0. So S0, as I mentioned before, S0 is 00 and S3 is 11. So now we declare S0 equals to 2-bit binary 00, comma, S1 is 2-bit binary 01, S2 is 2-bit binary 10, and S3 equals to 2-bit binary 11. Instead of using the binary type, you can also use the decimal. So you can just simply write S0 equals to 0, S1 equals to 1, S2 equals to 2, S3 equals to 3. So that also works. But now we stick with this type of declaration. So now we are entering the main body of our code. Okay, to describe the sequence from one state to another, we require the always block, and since each state has two possibilities, whether the input is 0 or the input is 1, so we need to have the if conditions. Okay, so first we need to have the always block that describe the whole system, and then we need to have the case statement. So for example, we have 4 cases. The first case is when the current state is S0. The second case is when the present state is S1, and then when the current state is S2, and finally when the current state is S3. So that is corresponds to the case statement. So inside the case statement, we need to have the if statement, if condition. So if in one particular state, so we have two possibilities, whether the input is 0 or the input is 1. So we begin with the always statement. So we can write always, and then these symbols, the @ symbol. So inside these braces, we have to list the sensitivity variable. So anything that happen to this variable, so the block must be executed. So the sensitivity list is basically the current state or the input. So as long as the either current states or X change, the block must be executed. So remember that we need to begin with begin before we write the content of the always block. Okay, now we have 4 cases. That is, the current state is S0 up to the current state is S3. So now we begin with the case statement. So case current state. So the first case is when the current state is S0. So we write this, the colon symbol. So we need to begin the first case with begin, because we have the content in this case is more than one line, so we need to begin with begin statement. And then since this system is basically the system is the more machines, so the output is attached directly to the state. So every time when the state is S0, the output must equals to 0. Sorry, this is where is 0 here. Okay, now we enter the condition, the if statement. So now, how to read this is first, now the current state or the present state is S0. So the output is 0 for sure. Now we have two possibilities, whether the input is 0 or the input is 1. If the input is 0, S0 goes to itself. If the input is 1, S0 goes to S1. So we write in this manner: if X is high, the next state is S1. Else, or if X equals to 0, the next state equal to S0, or we can also say the next state equals to the current state. So we end the first case with end. Okay, now we have accomplished in describing the first case, in which when the current state is S0. So we can proceed with the next case, which when the current state is S1. So we can just copy the first block and then we paste here. So now the second case is when the current state is S1. So the output is also 0 when the state is S1. So we can describe the flow from S1. That is, if the input is 0, the next state for S1 is S2. So we can write if X equals to 0, so the next state for S1 is S2. Else means that when the input is 1 other than this, so the next state is S1, or the next state is the current state. Okay, I forgot to mention about this symbol. The double equivalent symbols is the logical what do you call it? The logical equivalence statement. So an alternative way to write this is actually by removing all of this, and if we just write if bracket one variable, it refers to if the variable is high, go to the next line. So for the case of when x 0, we can replace this with by putting the symbol tilde. So this basically means if x is low, the next state equals to S2. Alright, so we proceed with case when the current state is S2. So simply the output is 0. So if the input is high, the next state for S2 is S3. If the input is 0, the next state for S2 is S0. And finally is the case when the current state is S3. So now here in S3 the output is 1 because it can be seen here clearly that the output is high only when the state is S3. So when the current state is S3, output is 1. If it doesn't matter whether you begin with x is high or x is low. So let's begin with if the x is high, the next state is S1. Else, or if x is low, the next state is S2. So we have accomplished our case statement. So we have 4 cases: current state S0, current state S1, when the current state is S2, and finally when the current state is S3. But we normally end our statement with the default case. So write default colon. So by default, so we always want our state goes back to the initial state with which is the S0. So we write default next state is S0. So we have accomplished our case block. So we have to end our case block with end case. END-CASE, end case. And we end our always block with ends. Since we begin our always block with begin, don't forget to write end down here to indicate the end of the always block. Alright, so we have accomplished the first block for our Verilog module, the first always block I mean. We need to have another always blocks. which is for the purpose of clock. We describe the transition from the current state to the next state when the clock reach its raising age. So we write the second always block. So I repeat, the purpose of this always block is to describe that when the raising age occurs, okay, the states must change from one to another. So in Verilog, the raising age is known as the positive age, or it's known as POSEDGE, positive age basically. So our sensitivity list is when the positive age happens or raising age happens, this block must be executed. So begin. So basically the only line that we want to say is when the raising age or the positive age occurs, the next state should be assigned as the present state. So how to say that is by using which is known as the non-blocking statement. So now the next state becomes the current state. So the current state is the next state. Okay, these symbols, even though it is very similar with the less or equal symbol, but in fact it is actually like the equivalence symbol, which is known as the non-blocking assignment, in which it is like an arrow, left arrow, you can say it. So next state goes to current state. Okay, but don't forget that we have one more input that we have not considered yet, which is the reset. Okay, so the next state becomes the current state as long as there is no reset. Okay, so how to describe that? So we add the if conditions. If there is a reset, okay, the current state should goes to S0, which is the initial state. Else means that if there is no reset, so we go to the normal process, which is the next state become the current state. Okay, so that's all for the second always block. So we end our block with AND. And then AND module. Basically we have accomplished our 101 sequence detector by using more machines. But there is worth to be noted that an alternative way to describe the value of output is, instead of placing it in each case, so we have y here equals to 0, y equals to 0 for when the current state is S1, y equals to 0 here when the current state is S2, and y equals to 1 when the current state is S3. We can actually summarize the output in a separate line. So let's say we don't want to use this. So instead of deleting it, let's just comment it. Commands. So it turns into green. So put the double slash. Okay, so instead of describing the value of y, we can write in a perhaps the more what you call the concise way, which is we say that. So we begin with assign what you call this statement. Assign y is high, okay, when the current state is S3. So note that we utilize the double equal symbol here to say that if these conditions is true, y will be assigned with high value, y equals to 1. If this statement is false, y equals to 0. So instead of describing this, and this, we can describe the value of y by using the separate line. Okay, now we can save our work. Maybe before we proceed with the test fixture, we discuss how do we construct the same system, yes, 101 sequence detector, by using the milli machines. So we right click here, add a new source, choose the Verilog module, so name our second file as milli 101. Okay, and maybe we can skip this step. Finish. So basically we already have our more module. So in fact we can just copy the content and modify it in our milli module. Okay, so we paste it here. Okay, now it is very similar between more and milli. We all also need these inputs, you know, clock and reset, and also output y. So here let's check our state diagram of the milli machines. So the only difference is we have one less number of states, and secondly, the output depends on the input. I mean, the output is explicitly depends on the input. Okay, so first and foremost, we can remove this state S3 because we do not require it. Okay, so but our current state and next state is still 2 bits because we have 3 states. And we can remove the S3 case. Okay, before this, what we have done in the more module is we describe the output directly attached to the current state. So when the current state is at 0, the output is 0. But for milli machines, the output depends on the current state and the input explicitly. So instead of putting the output here, we have to place the output after the if conditions. So if X is high, S0 goes to S1, yes, the next state is S1, the output is 0. Else, meaning that when the input is 0, the next state is the current state, we have to write the output is 0. So do not forget to put the semicolon. So since in each statement we have more than one line, we have to begin with begin. My mistake. Begin, and we have to end with end. Similarly in here, we end with end. Alright, so we proceed with this second case, in which when the present state is S1. So we have to describe the output in every if conditions. So here, if x is 0, the next state is S2 and the output is 0. And if the input is 1, the next state is the current state and the output is 0. So begin here, put begin here and end here. And finally, the case when the current state is S2, if the input is 1, the next state is S1, the output is 1, because we are describing this path from S2 to S1. So place begin and end. Else, meaning that from S2 when the input is 0, the next state is S0, the output is 0. So place begin and end as well. So we follow this line. So this end is actually the end for the always block. This end is actually the end for this begin, and then we specify the default statement. Okay, so we end this case block with end case, and this final end is referred to the always block. Okay, similarly, we need also to have the second always block to describe the transition from the current state to the next state. Okay, as I mentioned before, instead of specifying the output value in each if conditions, we can summarize it by using a single line like this. So in fact, we can remove this. How to do that? Remove this, here, here. Okay, now instead of describing the output in each if conditions, so we can summarize it in this line such that the output is high. Let's check our state diagram. The output is high for milli machines when the current state is S2 and the input is 1. So the way to describe it in Verilog is by writing y equals to whether the current state is S2 and the input is 1, so nx. So if you recall the Boolean expression for output of the more and milli machines, so there's a difference in which the inputs explicitly appear in the output equations. So if you compare these two equations, so for more machines, y directly depends on the current states only, but for milli machines, y depends explicitly on the current states and the inputs as well. So basically we can remove all these lines for more machines. So now we have our, so we do not forget to save your work. So we have our more module and also the milli module. So now we are ready to simulate our system. But before that, I forgot to mention one thing. Since in here we have opted to what do you call describing y in a separated lines, because before y is included in the always block, but now we have removed y from the always block and we describe y in a separated lines. So we are no longer required to declare y as the register. So we can remove this and save your work. And also we can remove the register declaration for y, even for the more module, because y, I repeat, because y no longer appear in the always block. Okay, alright, let's begin with the simulations. Okay, since we have two modules, okay, one for milli and one for more, let's begin the simulation with the more machines. So right click in here and choose the new source and select the Verilog test fixture, and let's name our file as more101 underscore tf for test fixture, and select the more module, more101 module. Okay, so in here we have the skeleton of our test fixture that corresponds to the more module, more101 module. So basically we can remove this, maybe remove everything because we want to start fresh. Okay, firstly, when we are thinking of simulating our sequence detector in particular, or any FSM, we need to know that what is the input sequence that we wish to test, and based on that, what the system is supposed to give and what is our actual results that we will get. Okay, so let's decide that. Let me write somewhere here. This is not the actual code yet. I just want to explain to you one thing before we proceed with the actual code. So I will utilize this space to write the content. Okay, first let's say we wish to test our 101 sequence detector with the sequence of let's say I want my x, the value of my x according to this sequence. Let's say I just write as a random sequence 0 1 0 1, okay, and then maybe 0 1 0 1 or 0 0 1 0 1 0 1 0 0 1 0 1, for example. Okay, this is the sequence that I want to test. Because I want to test my sequence detector by using this sequence. So I wish to get this kind of output because this is the 101 sequence detector. So I supposed to get the output sequence like this because this is 101. So I should get a 1 here, and then again this is as 101 as well. So 1 again, and then here is 101 one more time, so 1. So here no 101, no 101 up to here. Yeah, here we have 101 one more time, so here and finally here. So basically I expect to get 1 2 3 4, 5, 6. 6 pulse, 6 high in my output. So I expect to get this. Okay, but now how do I realize this kind of sequence in my test fixture? So let's comment this before I forgot to, because if we save our things and this appear here, it might lead to error. So firstly, the concept is if I have a constant, for example, let's say I have a constant. So I write my x equals to a constant, for example. Okay, it's supposed to be the value of x will be assigned with the value of the constant, but the problem will arise when x is 1-bit variable, but the constant is more than 1 bit. Okay, suppose that my constant is 1100. Okay, if I write in this manner, x equals to 1100 in binary, of course, 2-bit binary. Even though I write x equals to 4-bit numbers, but the system will only assign x with 1-bit number because we already declare x as a 1-bit variable. The question is, which number will be assigned to x? Is it the rightmost, the LSB, or the MSB? So the answer is the value of x will be assigned with the LSB of the constant. So now even though I write in this manner, but in fact I will only get x equals to 0. So that is one problem. Okay, so if I have a data, let's say my data equals to so how many number? 20. So 20-bit binary. Let's say I copy the whole things here in here. Okay, so if I have this data equals to this number, and then when I write x equals to data, when I write down here somewhere down here x equals to data, so my x, the value of x will be assigned with number 1, the LSB of the data, not the MSB of the data. So how to resolve this problem? So the way is, instead of writing our constant with our according to the sequence of our desired sequence, we have to write in the reverse manner. So the correct way is writing data in a reverse manner. So we write from the right of the sequence 1 followed by 0 followed by 1 0 until 0. So 20-bit binary 1 0 1 0 0 1 0 1 0 1 0 0 1 0 1 0 1 0 1 0. So the second line is the correct way to describe the constant or the data, because x will be assigned with the LSB, the rightmost number of multi-bit numbers. So we remove the first line. So now we have this data equals to 20-bit numbers. So we expect that x will be assigned with the numbers in the data from right to left. Okay, the second problem is how do we get the second number, the third number, and so on. So if we write x equals to data for the first time, x will be assigned with this 0. We wish to have, for the second time, x should equals to this value instead of the LSB. So one of the way is by writing data x equals to data shifted to the right, shifted 1 bit to the right. Okay, so the first line gives x equals to 0, which is the LSB. The second line gives x equals to 1, which is this number, this one. And then if I write this further, data shifted to the right, shifted 2 bit to the right, so I will get x is equals to this 0. Okay, so by using this idea, we can form a for loop. So basically, we can write something like we not even require the for loop. We just write, let's say, x equals to data shifted to the right. Let's say integer k or I or j, it's up to you. So k, if we begin k equals to 0, and then we write like this, x equals to data shift to the right about k bit, and we increase the value of k by 1. So we will get, we can assign the value of x from right till the left. Okay, so can remove this. So let's write in a proper manner. So firstly, we have to declare our data and our integer. So data can be declared as register. So since it is 20 bit, so we can write 19 up to 0 data, and then integer k, or you can use I or any variable. And then require the so let's give some tab here. Okay, so initial and then begin. Okay, in this initial block, okay, we will declare or assign the value of our constant. So we have the first constant is the data. So data is this number, and then k. Our k is begin with 0. Okay, remember that we also have the reset signal. Okay, so let's say reset is high. Let's reset first our system about let's say 40 time units. So since we are using the nanosecond scale, so this is in fact the 40 nanoseconds. And then let's reset. Let's has no reset for 160 time duration. Okay, and then finish. So we have finished our first initial block. So don't forget to end your initial block with end. Alright, so the second initial block is to assign the value or to generate the clock signal. Okay, so we create another initial block, and then this time we want to generate our clock. So clock initially, let's say, is 0, and then we want it to toggle along the simulations, or we can say forever like that. If we want the clock value always toggle from 0 to 1, and then 1 becomes 0, 0 and 1, such that we have something like a square wave to be assigned to our clock signal. Okay, so to realize that, we can utilize the forever block. So forever begin. Okay, so we have to decide for how long is the one period of the clock cycle. Let's say we wish to have 10 time units for one period, so it means 0 for 5 time units and 1 for another 5 time units. So let's write clock is 0 firstly for a time duration of 5 nanoseconds, and then after that toggle the value of the clock. Clock equals to what do you call this? The inversion or clock bar. So the next cycle of the forever loop is clock equals to 1, and then 1 for 5 unit time duration, and then 1 becomes 0 again. So this process will repeat again and again until we stop the simulations, in which up to 40 plus 160 time unit, which equals to 200 time unit or 200 nanoseconds, since we have 20 bit number in the sequence. So we end our forever block with end, and then end our initial block with end. Okay, next, the second important thing is to assign the value of x. So we want to utilize this idea. Okay, so for that purpose we build the always block. So always add. So now the sensitivity variable in the sensitivity list is supposed to be the clock, meaning that every time when the raising age occurs in the clock signal, x should be assigned with a new value. So the sensitivity variable is the positive age of the clock. So post EDGE, which refer to positive age or raising age clock. And then we begin our always block with begin. So now we can take this and transfer it to our always block. And we can remove this. So we can end our always block with end. And that's all for our test fixture content of the test fixture. So maybe we can remove this, and let's keep this for our reference, and let's write somewhere before the end module, perhaps, or anywhere in the code. Okay, so we save our work, and then let's run the simulations. So first of all, you have to ensure that you have chosen the simulation option instead of implementation, and then click on the test fixture file. Okay, first you can check the behavioral syntax, make sure everything is alright, and then run the simulation. Okay, let's check our input and output simulation results. In this tab, click the full view. So let's inspect first, but unfortunately the final 101 does not fully appear here. So maybe we need to extend our simulation time up to 210 perhaps. So let's redo the simulation. And let's change this, reset for 40 nanoseconds and no reset for the next 170 nanoseconds, and we save this test fixture again and rerun the simulations. Okay, now I expect we should get the high here. Yes. Alright, so let's check. What do we have here? So output Y, X is the input, the clock signal, the reset signal. This constant data and K it's not really required here, so we can remove it by pressing the delete button. Okay, let's rearrange our maybe no need to rearrange this, so this is fine. Output, input, clock, and reset. Okay, let's check. So initially we expect to get Y high in 1, 2, 3, 4, 5, 6 in 6 occasions. Okay, the first high is due to this 101, and then here, 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 and finally here. So 6 high in the outputs. But in the simulation we get how many high? 1, 2, 3, 4, 5. Only 5 high. The reason is the first 101 sequence, okay, is not counted because of the reset. You remember that when reset is high, or we can say that when we reset the system, any input will not influence the system. So this 101 basically is not counted. So it does not influence the input. So the input remains 0. And then this 101, okay, provide an output high here. But as can be seen here, the output is like a delay. So the duration of delay is 1 clock cycle. Because in order to the system to respond, it has to wait for the raising edge to occur. So if you notice here, this is the raising edge or the positive edge from 0 to 1. So Y will change its value when the positive edge occurs. So this is basically happen in the Moore system, but in the milli system we will get the difference, a little bit difference, output patterns. Okay, so we will see that later. So this high is due to 101, this high is due to this 101, and then this high is due to this 101 sequence, this is due to this 101, and finally this output is high due to this X101 sequence. Excuse me. Alright, so let's close this simulations and proceed with our the second simulation for our milli module. So the content is basically very similar, almost 100% similar. But we have to create a separate test fixture. Choose the test fixture. Now we are ready to simulate our milli module. So write milli 101 underscore TF, and now target the milli module. Choose this and finish. Okay, so in here we have the skeleton of our milli test fixture. Okay, so basically we can just copy the content in our Moore test fixture from line 43 up to before the end module. Okay, so we paste it here. So delete this and paste it here. So the only difference between this milli module and this Moore module is the computer generated code. In here we have milli, in here we have Moore. Okay, so save our work. Now we are ready to simulate our milli test fixture. Go to milli TF, milli 101 underscore TF, check the behavioral, and then run the simulations. Oh, my antivirus is blocking the simulation, so I have to disable it. Okay, I rerun my simulations. Sorry for that. Okay, let's inspect the results of our milli model, the 101 sequence detector using the milli model. Okay, so similarly, as can be seen here, the first 101 sequence is not counted because of the reset, as I mentioned before. Okay, now this output is high due to this 101 sequence. As can be seen here, the output is immediately triggered or changed to high, okay, without the need to wait for the raising edge. In fact, even though this actually coincidentally happened in the raising edge, but in fact for milli machines, the output is corresponds directly with the inputs. As long as there is the input 101, the system will respond immediately, even though the clock is not in the raising edge stage or condition. Okay, so so you can see maybe the drawback in the more machine is the delay in a real system. Okay, but since in milli machines the output is directly depends on the inputs, sometimes it is very sensitive with the noise, or we call it as glitch in a digital terminology. So every method, either more or milli, it has its own advantage and also drawbacks or disadvantage. Alright, so perhaps that's all for now. So thanks for watching.